Okay, let's pick up where we were last time. And we're just seeing that with the use of the variational theorem, we were able to take the orbital approximation, which we saw in the very first part of the lecture, that was just not a good approximation and gave us a 38% error in the energy. But when we used the variational approach and sort of adjusted our wave functions, we were able to get to a pretty good answer and still keep this orbital approximation. So this is an idea that chemists really like, the idea that you can think about individual electrons in their own orbits, and then you can think about individual electrons transferring and all that. Now you know the problem about indistinguishability of electrons, so you know fundamentally there's some issues, but it's not a bad approximation if you can get the right energies, and it gives you a good intuition about the chemistry that's taking place. So we're going to try to keep working with this, and knowing that we can sort of work the math in such a way that we're always careful about how we do this, and sort of run with this idea. And of course, as you know, in the idea for the helium atom, the ground state, if we can think about it as one electron in the 1s, the other one in the 1s, and as long as we make sure that it's antisymmetric, which is not something we sort of teach in freshman chemistry, we just sort of look at this part and say that's the electron configuration. But now we know, we're going to be a little smarter. We're going to have an proper antisymmetric wave function, but we are using the orbital approximation in writing this. And we're going to do some adjustments to sort of make these wave functions better and better. Now, as I said, this spoils the picture, but we're going to try to fix this. And sort of the idea to fix this came about really quickly, right? Around the time that Schrödinger had come up with his equation in 1927, Douglas Hartree had already started figuring out how to sort of do massive calculations for multi-electron atoms. And he took a very basic approach, which is what's called mean field potential energy approach, mean field theory, which is to take the charge of the nucleus and all the other electrons except for the one electron that you're trying to work on, find its wave function, and group all of that potential together into one sort of mean potential that one electron is moving in. So mathematically it looks something like this. The electron of interest, if I use an I there, is moving in the potential of the nuclear charge, but plus this guy, which is the Coulombic repulsion terms for the electrons, sort of averaged over all the other electrons' wave functions. So this is going to be sort of an iterative thing. So you do this for the first electron moving in the field of all the other electrons, then you do it for the second electron, you do it for the third electron, and when you do that, you end up with a whole bunch of refined wave functions moving in the mean fields, and then you just go back and do it again using the improved wave function for all the other electrons, resolve it for the electron of interest, and then go through all the electrons, and you do this over and over again, and eventually you converge on a mean field that is appropriate and gives you the right answer, or closer and closer to the right answer. So this mean field approach works, and there's all kinds of refinements, and I don't really want to get into it. We don't have time in this class, and I'm not sure that you guys are interested, but if you go on to that kind of career, then you can learn certainly a lot more about computational chemistry and how this kind of approach works. But the idea now is that we're just going to stick with this orbital approximation, and we'll be okay, because we know we have a lot of tools to help us stick with that model. And I love this picture, because this is a picture of Douglas Hartree here, and actually Phyllis Nicholson is a mathematician, and this is at Manchester University. So he was trying to solve the Schrödinger equation for the multi-electron atom. These are the days when people only had slide rules, right? Not even pocket calculators. And so this is an analog computer. It uses a bunch of gears, and you have sort of a bunch of workers there, all trying to sort of code this analog computer together so it will integrate the differential equations. So you can imagine the challenge of doing computational science back in those days. Okay, so what's nice about this picture is that it allows us to sort of confidently go forward with this idea, just like we showed in freshman chemistry textbooks, that the electron of interest is seeing an effective nuclear charge, which is screened or shielded by the electrons that are between it and the nucleus. All And one of the consequences of this is that screening actually depends upon the angular momentum of the electron of interest and also the angular momentum of the electrons that are between it and the nucleus. And we'll see how this all plays out. But you can imagine how this happens because we know that an s electron is going to spend more time closer to the nucleus, and a p electron, which has angular momentum, gets pushed away, right? And a d electron, which has higher angular momentum, gets pushed even further away. And so as these electrons get pushed further and further away, their probability of sort of being close to the nucleus gets lower. And so an s electron is going to see a much stronger nuclear charge than a p electron would because it's further out and there's intervening electrons that are going to be screening it. And a d orbital is going to be even further out, so those core electrons are going to do a much better job screening for a d than it would be screening for, say, an s orbital. All right? And so this is sort of the logic that gets us here, and that's the logic that gets us to sort of this level of understanding on how the energy levels go from, like, for example, when we were building up our electron configurations in freshman chemistry. So we learned that the n equals 2 orbitals were all degenerate, but now you see the p orbital, which has angular momentum compared to the s, which doesn't, gets pushed a little further out, so its screening by these electrons is less than, say, the screening of the 2s electrons by this 1s electron. So this gives us then this sort of staggering. The 2p is greater than the 2s. The 3s is below the 3p, which is below the 3d. So this staggering is just due to the fact that these guys are pushed further out and they see less effective nuclear charge than the ones that have lower angular momentum. In fact, as you can see, it pushes the 3d so far up that the 4s actually managed to come lower in energy than the 3ds. And that sort of explains then, when you're just building your electron configurations from the lowest energy up, why we fill the 4s before we fill the 3ds. Okay, now I think I said all this already, but the other thing I guess I'd point out, just reminded the language here, when we talk about core electrons, we're talking about closed shells. So all the orbitals associated with a given n value are filled. And then the valence shell is that outermost n shell where it's not completely filled. So those are the electrons that are going to be involved in chemistry, chemical reactions, whereas the core electrons generally they don't get involved in reactions, they just pretty much stay put when reactions are taking place. All right. So this brings us to, once we have this electron configuration picture and this understanding, we can now start thinking about the periodic table and effectively the periodicity of the properties of the elements. And this is something that Dmitry Mendeleev realized and was sort of the first one to successfully try to arrange the elements. Once we identified who the elements were of all the compounds that people were looking at, they identify which ones were actual chemical elements, was able to arrange them by mass. And when he did that, he realized that there was some periodicity that was taking place. So that there was a whole group that were metals, and then as they increased the mass, they became nonmetals, solids, and then they became gases, and then they went back to being metals, solid metals, and they became, as they increased the mass, they went back to being nonmetals, nonmetallic, and then gases or liquids and so on. So this periodicity with increasing mass is what he recognized. So he started organizing and placing properties that had elements that had similar physical properties on top of each other, and we started evolving towards a periodic table. And of course then Moseley realized in 1914 that now that he knew a little bit more about the structure of the nucleus, that if you put them by atomic number, that you get a much better table. And now we have the periodic table, and I guess things like vertical columns are called the groups, and when you're going up and down a group, they all have similar properties, like all the alkali, lithium, sodium, potassium, or alkaline earth, magnesium, calcium, strontium, or the chalcogenized oxygen, sulfur, selenium, and so on. So going down the group, then they have very similar properties, and then you have sort of the other groups. I'll put a periodic table up here, and you can see. So these are sort of the alkali group. Of course, hydrogen's sort of not quite really there. Depends if you like. If you've got a really high pressures, hydrogen is supposed to turn into a metal. And then you have the alkaline earth. Here are the chalcogenides, the halogens, but everything's organized so that the chemistry is very similar, right? This is why people, carbon-based life. People always speculate about silicon-based life because it's right underneath. You can imagine germanium-based life on some strange planet, I guess. Anyway, you have the periodic table. You've seen this before. There's some trends here that I think we can understand better, given what we know about solving the wave function for multi-electron atoms. So let's look first at atomic radii. So here is a plot of atomic radii, starting with hydrogen to helium, and then here's that's period 1. Here's period 2 elements, period 3. What happened to period 4? I think I made a mistake here. Okay, I think there's a typo there. But anyway, you see these elements as you, in a given period, you see that the atomic radii is decreasing. You see that here with from neon going to argon. So neon is down here, but then once you get past neon to sodium, and then magnesium and aluminum and silicon, it's decreasing as you move down. So what's happening is that the size generally decreases when you move across a period from left to right, and that's because the outermost electron that you're adding on are being more strongly attracted to the nucleus. Now when you go from left to right, the nuclear charge is also increasing, but then you're adding an electron. But that electron that you're adding is seeing a more stronger effective nuclear charge as you move from left to right. And the reason is reasonably simple here, is that when you move from left to right, the ability of those screening electrons to screen the nucleus gets less. So if your screening electrons are S, then they do a pretty good job. But then as you move further to the left, you start getting screened by P electrons, and they don't do as good of a job. And as you keep moving, when you start getting d orbitals doing the screening, they do an even worse job. And so as a result, the outermost electron just gets sucked more and more into the center towards the nucleus, and that's why the radius decreases. And of course, you also see that as you move down a group, like if I just looked at from lithium to sodium, potassium, it increases, but that should make sense. You're just adding more and more electrons, and n is increasing in those outermost ones, and it's just further out in orbit size, which we saw. Okay. So then let's look at, say, ionization energy, periodic trends in ionization energy. So if you look at something like sodium, if you have sodium which has a 3s1 configuration, so it's neon 3s1, if you take away an electron from it, it takes about 496 kilojoules per mole that you need to take the electron away. So this is a positive number because it means you have to add energy into this system in order to remove that electron. If you try to then take this guy here, which is now a neon configuration, and take another electron, well, now you're trying to bust open a closed shell, right? A closed neon-like configuration. And neon's a noble gas, and the reason they're noble gas is you don't break open a noble gas because that's take an electron away from a noble gas because you're breaking open a closed shell. And you can see that it goes up by almost an order of magnitude by taking that second electron off. And then when you get to the third one, well, okay, you've already busted open the shell, but still your attraction to the nucleus is going to be getting stronger and stronger because you're removing electrons whose job is to shield that outermost electron. And so it's going to be getting more and more coulombic attraction to the nucleus. It's going to take more and more energy. But you can see it's not an order of magnitude now, this time, compared to, say, the first one that broke open, this one here, which broke open the neon closed shell. Okay. So you can see, okay, these guys successively getting higher because their repulsions are going down, but there's that big jump when you break open the shell, when you no longer have valence electrons, and now you're creating another set of open shell that's with a lower n. So I think, so generally it's the valence electrons here. So most chemical reactions are on the order of hundreds of kilojoules per mole. They're not on the order of thousands or tens of thousands of kilojoules per mole, because that's just moving these guys around just takes so much energy, and it's a lot more easily done to have chemical reactions that are moving electrons off of valence shells than it is to try to get at any of these core electrons. Okay. All right. So that's ionization energy. Oh, and then I have these plots here I wanted to show you. So if you look at the sort of trends in these guys, you see that here's hydrogen, here's helium, here's lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. And you see that there's a general trend that these guys increase. So the ionization is going up as you move across a period there. And the same thing is here is when you get into the next period, you see the ionization is going up. And as you, of course, if you go down a group, so if you look, say, like helium, neon, argon, it's going down. If you look at those guys, you can see that it goes down as you go down a group, and it actually increases as you go across a period there. And these are sort of sensible based on what we saw for the radii, sort of similar kind of ideas that the energy is going to go up because as you move across, they become more strongly attracted to the nucleus. But there's some glitches here. So like for example here, beryllium is a little bit higher than boron, and that's because that it turns out that there are sort of some stability associated with half-filled shells. So beryllium is a 2s, it's a closed S subshell, and so when you try to open up that closed subshell, there's some extra stability that you have to overcome, from being in a closed subshell that causes this guy to be a little bit higher than boron. And the same thing happens here when you get to nitrogen. Nitrogen has a half-filled subshell, and it takes a little more energy to bust open that guy than it would, say, oxygen, which is already neither half-filled or filled, right? Okay. Electron affinity is another one that gets mentioned here in this discussion, and that's the sort of ability of an atom to actually take an electron, like in this case chlorine, take an electron to form an anion. And again, this is a negative number because that means that it actually energy is released in this process. So it tells us that chlorine will actually take an electron, make an anion, and give off 349 kilojoules per mole of this. All right, and so this more negative value, if you see a value that's more and more negative, that means it has a greater and greater attraction. So if this goes down, then the affinity is lower. If this gets more negative, then I should say, if the size of this number goes closer to 0, then it's less affinity. If it gets more and more negative, it has a higher affinity. Okay, so let's, and of course if it's unbound, then the delta E of 0. So the convention is to define the affinity as the negative of the energy released in the reaction. So if you don't get confused, make sure you get your signs right here. So the delta E for the reaction is the negative of the electron affinity. So if somebody tells you electron affinity of this is 349, you say, wait a minute, that's positive. There's a convention here. And for the reaction, it's a negative 349, but the actual reported value is the negative of that. Okay, so just a heads up on that one. Okay, and I think there, I'm going to, let's show this one last plot here. If we look at this for the affinities, you see sort of similar behavior in the sense that, you see that they do become smaller as you go down a group, but as you go left to right across the periodic table, it's not as clear cut as it is with the ionization energy, but you do have that whole business about half-filled and filled subshells being a little more stable. And so if you can take an electron and become half-filled, or take an electron and become a filled subshell, then that's probably going to have a more negative, slightly more negative affinity. All right. So again, the affinities become smaller down the group, and as you go across, it depends. Okay, so I already said this. So that the half-filled shells are a little more stable. So carbon has a greater affinity than, say, nitrogen, and of course halogens. All the halogens, which are only one away from a noble gas configuration, are going to have probably the highest affinities. There's a little weird thing actually with a little glitch with fluorine. Is kind of interesting. Fluorine It's also the same reason probably why fluorine is a weak acid, why HCl is a strong acid, is that there's a lot of electron repulsions in fluorine compared to chlorine, and that sort of makes it a little misbehaving along that and the trends for the halogens. Okay, and I think that's all I'm going to talk about for the moment. We're going to take a break, and then we'll pick up with the last part of this chapter.